For those folks who could not attend the factory acceptance test this week, I think being able to see this video is going to go a really long ways to understanding the ins and outs of the system, as well as a useful tool for reference for troubleshooting, installation, training, all the way up to operations. Having gone to some factory acceptance tests before, I really enjoy working with this team. We come from a lot of different backgrounds, a lot of different companies, but we're all working together on this one mission, and it's been a real pleasure.
Well, this process has been unique for me. It's been a great pleasure working with different organizations, and it's been very reassuring that those organizations have teamed together exceptionally well. That includes CRG, Crown Packaging, and Alliant Technologies, working directly with the Department of Defense, the Assembled Chemical Weapons Alternatives programs, and several of the contractors that support destruction of the chemical weapons in bluegrass.
In an effort to provide context to the rocket warhead containerization system, we will start this video with a high-level view of the M55 rocket line at BGCAP. The production line consists of 4 primary rooms: Unpack Area Room, also known as the UPA, the Explosive Containment Vestibule, also known as the ECV, the Explosive Containment Rooms, or the ECRs, and the Energetics Batch Hydrolyzer Room, or the EBH. To begin the process, stored pallets of M55 rocket assemblies are delivered to the UPA via Enhanced On-Site Containers, or EOCs. The delivered pallets are then unpacked and prepared to be loaded onto the production lines. As a note, the team is currently working on a new project in the UPA that will involve non-destructive examination of the M55 rocket assemblies to identify problematic munitions early in the process. More information will be available as this project progresses. From the UPA, M55 rocket assemblies are conveyed into the ECVs on line 1 or line 2. In the ECV, the upper half of the shipping and firing tube is cut and removed, exposing the M56 warhead, which is then cut and removed from the M67 rocket motor. Once separated, the M56 is then conveyed into the respective ECR, and the M67 rocket motor is conveyed into an adjacent motor pack room not shown in this illustration. As an additional note, the team is also working on a new vertical rocket cutting machine in the ECVs that will offer additional benefits for the cutting and containment processes. More information will be available as this project progresses. The rocket warhead containerization system begins as the M56 warhead enters into the respective ECR rooms. The RWCS is a custom-engineered production system that is made up of 3 primary elements. First is the automated production process. Second is the warhead storage containers, or canisters. And finally, the canister pallets, or skids. This system was designed and built through a collaborative effort to produce a safe and efficient production environment. The RWCS automated process is a unique parallel production line with double backflow, which we will illustrate in this video. Once in production, the system can be operated as a single production line or as parallel production lines. The RWCS process can be broken down into 3 distinct sections to better illustrate and visualize the product flow. The sections are canister infeed, warhead infeed, and then the double backflow. We will begin the RWCS process with the canister infeed, where empty canisters are first introduced to the EBH room and presented on the EBH pallet conveyors. The canister infeed process begins with 2 pallets positioned on the EBH pallet conveyors. 1 pallet is empty, and 1 is filled with 25 empty canisters. From there, a single canister is robotically depalletized or unloaded and placed in a waiting autonomous mobile robot, or AMR. The AMR will transport the empty canister to either line 1 or line 2 precision docking stations. The line 1 and line 2 robot then picks the empty canister and passes it through the ECR EBH airlock. In the ECR clean robot removes the canister from the airlock and places it into the crimp station. The canister is lowered into the crimp station, and the lower clamps are engaged to lock the canister into position. The canister top cap is then removed and ready to receive a processed warhead. The next process in the RWCS is referred to as the warhead infeed. Warheads are fed into the ECR1 or ECR2 rooms from their respective ECV room. Warheads are then punched and drained with existing BG cap equipment and rotated 90 degrees to orient the punched holes horizontally to the direction of conveyance. The punched and drained warheads proceed to the orbital wrapper station, where they will receive an initial containment wrap of polypropylene stretch film. This is an optional operation that the control room operator can enable or disable during production. Warheads are then loaded into the waiting canister in the crimp station. This is from the previous canister infeed process. The canister cap is reinstalled or inserted in the can. The canister is hydraulically crimped with 30 tons of force in 2 stroking actions that provides a complete 360-degree seal. The last section of the RWCS system is what we refer to as the double back flow. This is where we're now going to take the crimped and sealed canister and reverse the flow of production back to the pallet conveyors. The newly sealed canister in the crimp station is ejected and robotically passed back to the EBH, again via the ECR and EBH airlock. Scales in the airlock will record total product weight. The canister is then removed, placed in a barcode reader, and the bottom barcode of the can is read. The label station creates a serialized barcode and applies 3 labels: canister top cap, left side, and right side. The canister top barcode is then read to confirm positive placement. Once the canister top barcode is read, the canister is loaded back onto a waiting AMR. And the AMRs then transport the sealed canisters back to the pallet conveyor to be palletized or loaded. Once a pallet is filled with sealed canisters, it is then cycled to the pallet labeler and has 2 labels applied that provide pallet content summary information. Finally, the pallet will cycle out of the EBH gate and ultimately out of the plant into storage or final destruction. The pallet conveyor will cycle the pallets and the process will repeat. On June 2, 2020, we successfully passed the RWCS factory acceptance test held at CRG Automation in Louisville, Kentucky. The following video was recorded during the FAT and is a step-by-step walkthrough of the RWCS dual production line with double back flow. Shown here is the HMI, or human machine interface. This is a visual representation of the system and allows the operators to fully control all elements of the system. Here we are at the depallet station. The robot is depalletizing an empty canister to begin the process on the canister infeed. The robot places the canister in the waiting AMR. From here, the AMR will undock and will travel to line 1 or line 2. After loading the AMR, the depallet robot grabs the next canister and prepares for the next load to be delivered. Here's a good visual of the EBH room. The gray 2x6s on the floor represent the existing grout pads in the EBH room. This was done to ensure that the factory acceptance test closely represented the actual site conditions. The AMR approaches the precision dock, locking in place. A green LED signals a positive lock. Line 1 or line 2 robot lifts the canister and moves it toward the ECR EBH airlock. In reality, the airlocks have steel gates. In this simulated video, we're using red and green lights to indicate door opening or door closing. There will be a time pause as the canister passes through the airlock to simulate the door opening or door closing. This robot is the clean robot in the ECR room. It has just removed a canister from the airlock. The empty canister is placed in the crimp machine. The lower clamps will engage, locking the can in position. The canister is locked. The robot now removes the top cap. Now, starting the process from the Warhead end feed, the Warhead is being fed from an ECV room. As it passes through the punch and drain machine, it will come to the orbital wrapper, shown here. The orbital wrapper will begin to rotate. It will apply 3 layers of a polypropylene film. This provides an initial containment for the Warhead to prevent any liquid spillage. Once the wrap is complete, the cutter comes out and will cut the plastic free. The Warhead proceeds. The Warhead conveys to the end of this line, where it will be stopped in the exact position and picked by the agent robot. This is the agent robot picking the Warhead and moving it over to the crimp station. With the canister in the crimp station, the Warhead is now placed smoothly into the canister. Once the Warhead is in place, the cap is replaced or inserted. The crimp table will then, with 2 strokes, hydraulically press a crimp to finally seal the cap in place. Once crimped, the canister is ejected from the crimp station. The clean robot will then pick the canister, and the process will reverse in the double backflow fashion. Here the canister is being removed and placed back into the airlock. Once in the airlock, a scale will record the product weight. A custom top holder conveniently holds the canister while being weighed. Line 1 or line 2 robot in the EBH then removes the canister, passes the bottom of the can over a barcode reader, confirms the scan, and presents the can back to the label station. In the label station, 3 labels are applied, 1 on each side and 1 on the top. Once confirmed, the canister is placed in the waiting AMR, and the AMR will return to the pallet station. With a fully sealed loaded canister, the AMR now undocks and begins to travel back to the pallet station. The RWCS system, with 2 production lines in operation, is capable of producing 25 sealed canisters per hour. 4 AMRs are utilized in the EBH room, with 2 of the AMRs on backup in the event of a low battery. Here the fully sealed canister has returned to the docking station for the pallet robot. AMR will dock and lock into the precision docking station. The robot retrieves the canister, moves it towards a barcode reader to read the top label, and then places the canister into the waiting pallet. Canisters are placed in the pallets in a very specific sequential order to ensure that the end-of-arm tool has access to all the various openings. As the factory acceptance test progressed, here we show the 25th Warhead approaching palletization.
25 is approaching the docking station. Once it's loaded, the trays will rotate. Okay. 25 is in the robot. It will stand. Moving to the skid, and mark, 25.
And now, the 25th canister is loaded and complete. Once loaded, the pallets will cycle. The timed run was 57 minutes. The fully loaded pallet now cycles to the pallet labeler. At the pallet labeler, a label is applied that denotes all the contents, serial numbers, and barcodes of the 25 canisters loaded on it. A label is placed on two sides to ensure that operators can visually see this when in storage. Now this is the pallet now being transported through the EBH gate onto the tray transfer room. The empty pallet cycles over to the pallet station, and the next waiting pallet with 25 empty canisters cycles into position. To simulate 25 empty canisters being brought back in, we reuse the pallet from the previous operations. This would now represent a new pallet of 25 empties being staged so that the cycle can repeat without stopping production.
To better understand the system that we have is ultimately going to go into a training facility that we'll be able to actually walk in, walk around, operate, and train our operators, train our mechanic personnel on them. Having a training, this unit that we demonstrated today within our training facility is going to be an asset to the 2 units that we install within the plant.
I think seeing that timed run for the automated step for the 1 hour duration, the kind of endurance cycle, was a pretty important milestone to see that it has the legs to go day in, day out, and to operate for the amount that it's going to be required to.
I think this is an exceptional opportunity for the program. It's a demonstration of a new process. We'll be able to duplicate this process in the chemical weapons destruction program and then destroy the rocket stockpile at Bluegrass.
The second key element in the RWCS system is the custom designed and engineered canister. This shows the design details put into the canister and an overview of the features and benefits of some of those designs. As previously mentioned, the top cap is made of aluminum to improve thermal transfer in the SDCs. Overall, this is a robust and repeatable sealing method. It's a simple and effective construction. The design allows for ease of automation for assembly and disassembly. Specifically, there were no consumables used in this design, such that there are no consumables in the ECR. The top cap offers the Warhead stability as well as a metal-to-metal contact to optimize the thermal transfer of heat in the static detonation chamber for processing speed. The top cap also incorporates 3 O-rings with a steel radial crimp. The top cap has a chamfered end, as well as the top of the tube has a chamfered internal section. This facilitates the ease of insertion of the top cap during the automated assembly process. The steel tube is a drawn-over mandrel, or DOM, seam tube, which offers excellent dimensional stability and has smooth interior surfaces for good O-ring sealing. A double-wall corrugated disc is an engineered flow control device. This is what allows the agent robot will place the warhead into the empty canister for a controlled descent to the lower part of the can. A bottom spring provides vertical counterforce to ensure the warhead maintains a metal-to-metal contact with the top cap. And finally, the bottom is a welded plate construction. This prevents any agent permeation over time. The completed assembly has passed rigorous packaging tests to include drop testing, vibration testing, and leak testing.
Next, go ahead and start 15 psi for 2 minutes. What we're looking for are any bubbles that came out. All right, so we're at 2 minutes. Don't see any bubbles, so we're cranking up to 50 psi.
We're at 5-0 now, and there's no leak. Understand, 5-0 psi and moving.
Okay. You good?
Because the crimp design detail of the canister is important, we thought we would show you the step-by-step process that takes place in the crimp station. The first step, the canister is inserted into the crimp table, shown here in step 1. The robot end-of-arm tool will grip and remove the top cap. The second step is the agent robot will place the warhead into the empty canister. The warhead rests on the flow control cardboard device for a controlled descent into the canister. Step 3 has the clean robot, which removed the cap in step 1, replace the cap, press and seating the cap firmly onto the top of the canister. Step 4, the crimp will then engage, and in 2 actions will crimp the device around the canister to provide a 360-degree seal with overlapping sections. Step 5, we'll release the lower clamps and eject the canister. Step 6, the clean robot will remove the sealed canister. Step 7, we'll repeat the process starting over step 1 and placing an empty canister back into the crimp station. The last and final piece of the RWCS system is the custom engineered and designed pallet, or skid. Shown here are some general features that will help you better understand the importance of this device in the RWCS system. It is precision engineered and fabricated for a fully automated robotic loading and unloading. It can safely and securely hold 25 M56 canisters. It is of welded and formed steel construction. The pallet is designed with a 17-gallon liquid containment tray. 2 pallet labels identify pallet contents. It was designed with 4-sided forklift handling. Each enhanced on-site container can hold 2 pallets. It has a removable bar for strapping the pallet to flatbed transports for on-site transportation. The chamfered corners on the lower side of the skid allow for conveyance on all the existing BG cap conveyors. There is no coating or painting. This is of raw steel construction. Design features on the top of the skid allow for ease of stacking pallets. This design can be stacked 3 high.
I've been lucky that since I've joined, we've been kind of fine-tuning this step to really get to this final optimal solution. I understand there was a lot of ideas thrown out, and I think really the best idea won. We have a pretty good process, and working together to come up with this optimal solution has been really productive.